Right, this is questions on electric fields. Question 1. We're asked to find the size of the force of attraction between a proton and an electron in a hydrogen atom with the given separation of 5.3 times 10 to the power of negative 11 meters. That should be a power, of course. This here should be epsilon naught, which is a constant of proportionality, the permittivity of free space. That's to the power of negative 12. And what is missing there, of course, is the unit, farads per meter. So we'll just add that in. There we go. So how do we do this? Well, we use the, of course, the kind of force involved will be the Coulomb force. And the equation you need to remember is charge 1 times charge 2 divided by 4 pi epsilon naught multiplied by the distance between them squared, r squared. So we sub this information in carefully. The charge, of course, for the proton is the same, but a positive value, as the electron charge, which is given up here as 1.6 times 10 to the power of negative 19 coulombs. So basically that number squared divided by 4 pi times 8.85 times 10 to the power of negative 12, that number there, multiplied by this radius or distance squared. And if you do this properly in your calculator, like hopefully I have done, you should be getting 8.19 times 10 to the power of negative 8. Now that's newtons, of course. So check that out, see if you get that. Question 2. A charge of positive 1.6 times 10 to the power of 19. Again, it's a power, negative 19 coulombs. Has a force of 8.7 times 10 to the power of negative 15 newtons exerted on it when placed at a point in an electric field. Find the strength of that electric field at that point. So we need to use the relationship between force, charge and electric field strength, which is simply force per unit charge, definition of an electric field in fact, and plug those numbers in. So we have the 8.7 to the power of negative 15 divided by the 1.6 to the power of negative 19, and you should be getting 5.4 times 10 to the power of no, it's a positive 4, of course, yes. And the units, now newtons per coulomb is the unit for electric field strength. Question 3. Find the electric field strength 20 centimetres from a charge of 15. Now the missing symbol here is micro. Once again, the software doesn't like the Greek letters, so microcoulombs. And that, of course, is 15 times 10 to the negative 6 of a coulomb. We use the equation for electric field strength that's relating to a point charge Q. Q divided by 4 pi epsilon naught times r squared. Plugging those numbers in, making sure we're using 15 times 10 to the negative 6 for the charge Q on top. If you plug that in, divided by 4 pi epsilon naught times 0.2, make sure we do 0.2 for the radius of a meter squared. Must use SI units, so you must use meters for the distance. And plugging that number in, you can get 3.37 times 10 to the power of 6 newtons per coulomb for the electric field strength. Question 4. The electric field strength between a pair of plates of length 4 centimetres and a cathode ray tube is 2.3 times 10 to the power of 4, that should be. So that's 2.3 times 10 to the power of 4, if you like, 23,000 newtons per coulomb. An electron enters the field at right angles with a velocity 3.7 times 10 to the power of 7, again that should be, meters per second as shown. So it's not shown, I will sketch the diagram for you. This is the positive plate, this is the negative plate. Here's the electron, comes along, enters the area of the plates. This length, of course, is given as 4 centimeters from the beginning to the end. And that pretty much does the diagram. So that's the situation. We're asked to find the velocity of the electron when it leaves the field. Now, of course, being an electron, it will be attracted towards a positive plate and then leave at a particular angle here, which we need to find, as well as the magnitude of the velocity v. Now, to do this, we can break it into the vertical component of velocity, call it vy, and also the horizontal vx, and relate them to v by Pythagoras. So starting with what we do know already, things like Vx will remain constant and it will equal the distance, which is 4 centimeters travelled over the time taken t. Now that velocity will be constant the whole time. It's not influenced at all by the field. So we can find time straight away actually just by rearranging this and dividing the distance 4 centimeters by the initial velocity, and that will be the same as Vx, of course. So if we do that and plug the numbers in, we get time equal 0.04, that's 4 centimeters in meters, over the initial velocity 3.7 times 10 to the power of 7. Oops, it's a 7 there. We get 1.08 times 10 to the power of minus 9 seconds for the time. That's the time that the electric field acts on the electron. And of course, during that time, it will exert a force. And we assume the gravitational force is negligible because the electron mass is so tiny, to the power of negative 31, so that effect will be negligible compared to the Coulomb force, which we can work out now, as equal to the electric field strength times the charge Q. Because it's a very strong electric field, 23,000 newtons per coulomb, and we're going to get quite a large number here, times the charge of 1.6 times 10 to the negative 19, of course. And what do we get? .68 times 10 to the power of negative 15 newtons. Now that's many orders of magnitude larger than the the gravitational force, because of the small, tiny mass of the electron, of course. From that, we can calculate the acceleration experienced by the electron when it's in that field, simply dividing the F, the force, by the mass of the electron, 9.1 times 10 to the negative 31 kilograms. So we get a very large number for the acceleration, 4.4 times 10 to the power of 15 meters per second squared. So a large acceleration. So the only thing is it only acts for a very short time of 1.08 nanoseconds. So it doesn't have a huge effect on the velocity. So now we have those figures, we can calculate the velocity component, Vy equal to Uy, the initial, which was 0 of course, plus At. So 0 plus the acceleration number 4.04 times 10 to the power of 15, negative 15. So no, it is positive 15. Yes, it is positive 15, of course. So that number times 1.08 times 10 to the power of negative 9. And we get 3. No, we don't get 3. Oops. Do that again. Yes, 4.37 times 10 to the power of 6 meters per second. Now that's the vertical component Vy. Now of course V squared equals Vy squared plus Vx squared, and therefore if you plug those numbers in and square root the final answer, you should get 3.73 times 10 to the power of 7 meters per second for the velocity. And the angle, well, we use tan inverse of Vy, that'll be our opposite side over Vx, our adjacent side, and you get 6.7 degrees for that angle above the horizontal. Just refer back to the first diagram for that. Okay.